My dear students, in this video, I am going to explain you the concepts of integral calculus in a simplest manner. Here you will get to learn how the integral calculus is used, how you can apply integral calculus in physics problem. So don't skip and keep watching carefully till the end of the video. Before we learn how we can use integral calculus, we need to know what integral calculus is. We have already learned about the differential calculus. Integration is the inverse process of differential calculus. To explain integration, I use a graph here. We consider y is the function of x and there are 2 points P and Q on the curve. We draw two perpendiculars on x-axis from point P and Q respectively. These are QR and PS. The value of x at point S is A and at point R is B. To calculate the area of PQRS, we divide SR into n number of equal parts, each of length del x. Here del x is equal to B minus A by n. Here we get n number of rectangular bars and we neglect the curvature of upper part of each bar. The value of y for PS is y is equal to function of a here because the value of x at point S is a. The area of the first rectangular bar is function of a into del x. Similarly, the area of second rectangular bar is function of a plus del x into del x. For second part, value of y, this is function of a plus del x. Therefore, the area of nth rectangular bar is function of a plus n minus 1 into del x into del x. The x coordinate of the second last vertical line is a plus n minus 1 into del x. Therefore, the corresponding y is equal to function of a plus n minus 1 into del x. So the area of n rectangular bar are the addition of all the rectangular bars here. Therefore, we can write this is equal to summation of function of xi into del x, where I is a general number from 1 to n, but the area of all the bars is not exactly equal to the area under PQRS. Actually, we have not considered the small triangular parts just above each bar. To neglect those triangle, we have to consider del x tends to 0. Then we can write the area of PQRS as limit del x tends to 0 summation of y, that is function of xi to del x, I is from 1 to n. This is equal to integration a to b fx dx, where a is lower limit and b is the upper limit of integration. If y is function of x and y is equal to x to the power n, then integration of y with respect to x, here integration x to the power n dx, this is equal to x to the power n plus 1 by n plus 1 plus c, where c is the integration constant. This is the basic formula of integration. I give you an example here. Suppose y is equal to x to the power 3, then integration of x to the power 3 dx. Here we compare 3 as n of the basic formula, then here we can write x to the power 3 plus 1 by 3 plus 1 plus c. Therefore, integration of x to the power 3 dx, this is x to the power 4 by 4 plus c. Why we use integration constant here? If we differentiate x cube or x cube plus c, where c is the constant, then in both cases we get same result, that is d dx of x cube, this is equal to 3x square, and d dx of x cube plus c, this is also 3x square, because differentiation of c with respect to x, that is 0. We have learned that integration is the reverse process of differentiation. Therefore, if we integrate the term 3x square, then we should get x cube plus c. Here 3x cube by 3 plus c, this is x cube plus c. Here c is the integration constant. As c is indefinite here, then it is called indefinite integration constant. For definite integral, we use limit. If integration x to the power 3 dx from a to b, then it is definite integral. And here the constant is not required, and we can write x to the power 4 by 4 from a to b, and we use here upper limit and lower limit in place of x, that is 1 by 4 upper limit minus lower limit. So whenever we are integrating for a specific range or specific value, then that integration is known as definite integral, and here constant is not required. Integration of some algebraic functions. If we integrate a x to the power n with respect to x, where a is constant, then we can take out a and write integration x to the power n dx, and this is a into x to the power n plus 1 by n plus 1 plus c. Integration of a dx, where a is constant, then this is equal to a into integration dx. As we know that if we integrate y with respect to x, then y should be function of x. Here we can write a into x to the power 0 dx, then this is a into x to the power 0 plus 1 by 0 plus 1, that is ax plus c. Integration 1 by x dx, this is equal to log x plus c. Integration e to the power x dx, this is equal to e to the power x plus c. Integration of e to the power ax dx, where a is constant, let ax is equal to z. Then we can differentiate this equation with respect to z, then a dz of x is equal to d dz of z, that is 1. Therefore dx is equal to dz by a. Then we can write integration e to the power ax dx, this is equal to integration e to the power z, and replacing the value of dx in terms of dz here, that is dz by a. Therefore 1 by a integration e to the power z dz, this is equal to e to the power z by a. So this is e to the power ax by a plus c here. Integration of some trigonometric functions. Integration of sin x dx. This is equal to minus cos x plus c. Integration of cos x dx. This is equal to sin x plus c. Integration of sec square x dx. This is equal to tan x plus c. Integration of cosec square x dx. This is equal to minus cot x plus c. Integration of sec x tan x dx. This is equal to sec x plus c. Integration of cosec x cot x dx. This is equal to minus cosec x plus c. If we differentiate cos x plus c, where c is a constant, then ddx of cos x plus c, this is equal to minus sin x. Differentiation of c with respect to x, that is 0. Then we can write d of cos x plus c, this is equal to minus sin x dx. Now integrating both sides we get, here differentiation is the reverse of integration, so the result of left side of equation, this is cos x plus c, and this is minus sin x dx. Therefore we can write integration sin x dx, this is equal to minus of cos x plus c. Similarly, we can prove the other trigonometrical equations. Some common rules of integration. If u and v are both of function of x, then integration of u plus v dx, this is equal to integration u dx plus integration v dx. Suppose integration of 2x square plus 3x with respect to x, this is, we can write integration of 2x square dx plus integration 3x dx. Then this is equal to 2 into x to the power 3 by 3. Here we consider the basic formula, that is integration x to the power n dx. This is x to the power n plus 1 by n plus 1 plus c. Here we consider 3 as n, and integration of 3x dx. This is 3x square by 2. Therefore this is 2 by 3 into x cube plus 3 by 2 into x square plus c, where c is the integration constant. Similarly, if u and v both are function of x, then integration of u minus v dx, this is equal to integration of u dx minus integration of v dx. We can interchange the upper limit and lower limit of a definite integral. Suppose integration a to b x square dx, we can write it as minus of integration b to a x square dx. We can insert any intermediate limit between the upper limit and lower limit of integration. Suppose integration of a to b x square dx, we can write it as integration of a to c x square dx plus integration of c to b x square dx. I think you got the idea how to use integral calculus. Next part of my video is the application of integral calculus. In motion related problem, to calculate velocity from acceleration and displacement from velocity, we can use integration. But the condition is velocity, acceleration, these should be function of time. If acceleration is function of time, then we can write a is equal to d dt of v, then dv is equal to a dt. Therefore, integrating both sides, we get v, this is integration of a dt. To get velocity from acceleration, we need integration. Similarly, if velocity is function of time, then we can write v is equal to d dt of s. Therefore, ds, this is equal to v dt, and integrating both sides, we get s is equal to integration of v dt. Therefore, to get displacement from velocity, we need integration. I give you an example here. Suppose the acceleration of a particle A, this is k t square, where k is constant and t is time. Calculate velocity of the particle at t is equal to 2 seconds starting from rest. As acceleration is function of time, then we can write A is equal to d dt of v. Therefore dv, this is k t square dt. Now integrating both sides of equation, that is integration dv, as k is constant, then we can write k integration t square dt, and putting the limits here, that is at t is equal to 0, particle is rest, so velocity is 0, and at 2 seconds t is equal to 2, velocity is v. We know that integration of dx, this is x, because we can write it as x to the power 0 dx, then here x to the power 0 plus 1 by 0 plus 1, this is x. Similarly, integration dv, this is v, that limit is 0 to v, and here k integration t square, that is t to the power 3 by 3, and limit, this is 0 to 2. Therefore v, this is k by 3, 2 to the power 3 minus 0, that is 8 k by 3 unit. To calculate area of a graph, we can use integration. Here a graph is given as y is equal to x square. Calculate area of the graph from x is equal to 1 to x is equal to 2. This is x is equal to 1. Suppose this is x is equal to 2. We have to calculate the area of this part. To calculate the area of that graph, we consider an elementary part of that area at a distance x with thickness dx. The value of y of that elementary part is y is equal to x square. Therefore, the area of that elementary part is dA. This is equal to y dx. This is x square dx. To get the entire area, we have to integrate this part. Therefore, integration dA. This is integration x square dx. And when x is equal to 1, area is 0. When x is equal to 2, area is a. Integration dA, this is a, and here x square, this is x cube by 3, and the limit is 1 to 2. Then putting the limits here in place of x, that is upper limit minus lower limit. So this is 8 minus 1 by 3 equal to 7 by 3 square unit. We can calculate the value of a variable physical quantity over a range by using integration. I give you three examples here. I have taken three bodies here. One, that is rod of length L, second one is disc of radius r, and third one is solid sphere of radius r. In each case, we have to calculate the mass of that body. Here, mass per unit length of rod, that is given as lambda is equal to kx. K is constant and x is the distance of rod. Similarly, mass of unit area for disc is given, that is sigma. This is equal to kx. Here k is constant and x is the distance from its center. And for solid sphere, mass per unit volume is given, that is rho. This is equal to kx. K is constant and x is the distance from center. To calculate mass of the body, at first we have to consider elementary part of it. Then we have to calculate mass of that elementary part. Then integrate that mass and we will get overall mass of that body. So for rod, we are considering an elementary part at a distance x with thickness dx. We can say that disk is consist of lots of concentric rings. So we consider here a ring of radius x with thickness dx. We can consider the solid sphere can be made of concentric spherical shell. Therefore, we can take a spherical shell as an elementary part. Hence, I consider a spherical shell of radius x with thickness dx. It should be noted that as the mass distribution are function of x in all cases, we consider the elementary part at a distance x here. Therefore, for rod, the mass of that elementary part, that is dm, this is lambda into dx, as m by l is lambda here. So dm is equal to lambda into dx. For disk, the mass of that elementary part dm, this is equal to sigma into dA. Here dA is the area of that elementary part. If we cut the ring and stretch it, it forms a rectangular strip with length 2 pi x and thickness of dx. Therefore, the area of that elementary part, that is 2 pi x into dx. For spherical shell, the elementary mass dm, this is rho into dv, where dv is the volume of that spherical shell. Here dv is equal to area of that shell into thickness. Surface area of that shell of radius x is 4 pi x square and thickness is dx. Therefore, volume is 4 pi x square dx. Now, in each case, if we put the value of mass distribution for rod, dm is equal to kx dx. For disk, dm is equal to kx into 2 pi x dx. This is 2 pi k x square dx. And for spherical shell, dm is equal to kx into 4 pi x square dx. This is 4 pi k x cube dx. Here in all cases, the elementary mass is function of x. Now we can integrate this to get the entire mass of all bodies. For rod, integration of dm, this is k is constant, therefore integration of x, and the limit is 0 to L. When length is 0, mass is 0, and when the length is L, total mass is m. For disk, integration dm, here 2 pi k, this is constant, integration x square dx. Here x varies from 0 to r, that means radius of that disk. Similarly, mass is 0 to m. For solid sphere, total mass, that is integration of dm, this is 4 pi k integration x cube dx. Limit is same, 0 to r, and here 0 to m. So mass of the rod is m is equal to k x square by 2, and limit is 0 to L. Here mass of the disk, that is m 2 pi into k x cube by 3, limit is 0 to r, and mass of the solid sphere, that is m 4 pi k x to the power 4 by 4, limit is 0 to r, and simplifying it we get k l square by 2 2 by 3 pi k r cube, and here pi k r to the power 4. I think you got the idea how you can apply integral calculus in physics problem. There are different videos on the application of integral calculus in my YouTube channel. You can watch these videos to get clear concept of integral calculus. Don't forget to subscribe our YouTube channel and also visit our free website Koushi.in to get various concepts of physics for your competitive exam.